Finally, we evaluate limits involving the classes of functions discussed in this lecture. In particular, we will be referring to their graphs for most of the examples. First, let's evaluate the limit of the inverse cosine of e to the x over 2 as x approaches 0. We begin by determining what the inner function approaches. We recall that the natural exponential function is continuous everywhere, so the limit of what's inside is just e to the 0 over 2 or 1/2. Now, the inverse cosine function is continuous on its domain, which is the closed interval -1 to 1. So in particular, it is continuous at 1/2. Note that the function is continuous at -1 only from the right and continuous at 1 only from the left. But it's continuous at 1/2. So we may just substitute in this case. The limit of inverse cosine of e to the x over 2 is just equal to the inverse cosine of e to the 0 over 2 or 1/2. And the inverse cosine of 1/2 is again the angle in 0 to pi whose cosine is equal to 1/2. So this must be in quadrant 1. X coordinates 1/2. So this angle must be pi over 3. Next, let's evaluate the limit of the sine of inverse tangent of x squared as x approaches -infinity. Again, we will start with the innermost function. Now, as x approaches -infinity, x squared approaches +infinity. So for this example, we will now need the graph of the inverse tangent function. I hope you have your collection of graphs with you for reference. But for this video presentation, I will display the necessary graphs here. Okay. Again, as noted earlier, as x approaches -infinity, x squared approaches +infinity. What can we say then about the inverse tangent of x squared? Since the expression inside the inverse tangent approaches +infinity, then we deduce from the graph of the inverse tangent that inverse tangent of x squared approaches pi over 2. Do you get it? And therefore, the sine of inverse tangent of x squared approaches the sine of pi over 2, which we know equals 1. Therefore, the limit of the sine of the inverse tangent of x squared as x approaches -infinity is 1. So for these examples, we will first observe the behavior of the innermost function and then proceed outward. If a function is continuous at the limit of what's inside, then we just substitute that value. If not, then we might need the graph of the function. Next, let's compute the limit of the inverse tangent of ln of x as x approaches 0 from the right. Note that the ln function is undefined at 0. So we will use the graph of the ln of x, and we will also use the graph of the inverse tangent of x. Recall that the ln function is a logarithm with base, is a logarithmic function with base greater than 1, so its graph looks like this. All right. Again, we begin with the inner function. As x approaches 0 from the right, what happens to the ln of x? Well, it decreases without bounds, so we write ln of x approaches -infinity. So the expression inside the inverse tangent approaches -infinity, and based on the graph, inverse tangent of ln of x then must approach -pi over 2. And that's it. The limit that we are computing is equal to -pi over 2. Next, consider the limit of the inverse cotangent of 2 to the 1 over x as x approaches 0 from the right. Note that as x approaches 0 from the right, 1 over x approaches positive infinity. So we will need the graph of the exponential function f of x equals 2 raised to x. You will also need the graph of the inverse cotangent function. Note that 2 to the x is an exponential with base greater than 1. So the graph of f of x equals 2 to the x looks like this. Now it rises from left to right. Again, we proceed from inside out. So as x approaches 0 from the right, 1 over x approaches positive infinity. So the exponent of 2 approaches positive infinity. Therefore, 2 raised to that exponent also approaches positive infinity from this graph. What can we say then about the inverse cotangent of 2 to the 1 over x? Well, since the expression inside approaches positive infinity, and based on the graph of the inverse cotangent, this approaches 0. Remember, the equation of the x-axis is y equals 0. Therefore, the limit of the inverse cotangent of 2 to the 1 over x as x approaches 0 from the right is 0. Now, in our next example, we replace the inverse cotangent function by the cotangent function and let x approach 0 from the left this time. Again, the exponent here approaches negative infinity. So we will need the graph of f of x equals 2 raised to x once more. Now, as x approaches 0 from the left, 1 over x approaches negative infinity. So, based on the graph of f of x equals 2 to the x, since the exponent approaches negative infinity, 2 to the 1 over x will approach 0. So, cotangent of 2 to the 1 over x approaches cosine 0 over sine 0. But cosine of 0 is 1 and sine 0 is 0. So, this limit is going to be infinite. And we need to determine whether the denominator approaches 0 through positive or negative values. So we need further information. Okay. Now, going back to this step, 2 to the 1 over x approaches 0. But in particular, as the exponent approaches negative infinity, the exponential approaches 0, but it approaches 0 from above. So we write 2 to the 1 over x in particular approaches 0 from the right, or from approaches 0 through values that are greater than 0. Now, what does this mean? Okay, so let me just draw a unit circle here quickly. Okay, so what does the expression inside the cotangent approaching 0 through values greater than 0 mean? Well, means that we have an angle which approaches 0 from the first quadrant. Okay, so 2 to the 1 over x approaches 0 through values in the first quadrant. And in the first quadrant, the value of the sine function is positive. Therefore, cotangent of 2 to the 1 over x approaches something of the cotangent of 2 to the 1 over x will be of the form 1 over 0 passing through positive values, so it approaches positive infinity. And thus, the limit that we are computing is positive infinity. Next, let's evaluate the limit of 2 to the x plus 6 to the x over 6 to the x plus 5 to the x as x approaches positive infinity. Due to lack of space for this slide, and I want to keep the solution in just one slide, I will not provide the graphs here anymore, but we'll just recall that when the base of an exponential is greater than 1, the limit of a to the x as x approaches positive infinity is positive infinity. And when the base is less than 1, then this limit is 0. Okay? Now, in this expression, the bases are all greater than 1. So the limit of each of these as x approaches positive infinity is positive infinity. So we have something of the form infinity over infinity. Now, how do we remove the indeterminacy? Recall our technique for limits of rational functions at infinity. We multiplied and divided by the reciprocal of the highest power of x in the denominator so that we obtain in the denominator the sum of a non-zero constant and negative powers of x, all of which approach zero as x becomes infinite. The technique here is similar. We will multiply and divide by the reciprocal of the term in the denominator that becomes infinite the fastest, no? Or that, yeah, that becomes infinite the fastest, or that is the greatest, no, among all the terms in the denominator. In this case, 6 to the x, the exponential function with base 6 grows much faster compared to the exponential function with base 5. So the trick is to multiply and divide by 1 over 6 raised to x, or 6 raised to negative x. Okay, and then let's see what will happen. We distribute first. So we have the limit as x approaches positive infinity of 2 to the x over 6 to the x, which combines as 2 over 6 raised to x, or 1/3 raised to x, plus 6 to the x over 6 to the x, or 1, all over 6 to the x over 6 to the x, or again 1, plus 5 to the x over 6 to the x, which combines as 5 over 6 raised to x. Note that the base of this exponential is now less than 1, and the base of this exponential is also less than 1. So as x approaches positive infinity, these approach 0. Therefore, this limit is equal to 0 plus 1 over 1 plus 0, or 1. So the principle is to multiply and divide by some exponential expression so that the denominator becomes a non-zero constant plus expressions that approach 0. For instance, let's consider the limit of e to the negative x minus 2 e to the 2x all over 3 e to the negative x plus 2 e to the 2x as x approaches negative infinity. Now, as x approaches negative infinity, note that negative x approaches positive infinity, while 2x approaches negative infinity. So let's recall the behavior of an exponential function with base greater than 1 as its exponent approaches positive infinity or negative infinity. Okay, so since the base is greater than 1, we recall that the limit of e to the x as x approaches positive infinity is positive infinity, and the limit of e to the x as x approaches negative infinity is 0. Now, going back to the limit that we are computing, note that negative x approaches positive infinity as x approaches negative infinity, so that these terms approach positive infinity. Meanwhile, 2x approaches negative infinity, so that these terms approach 0. Okay, so we have something of the form infinity minus 0 over infinity plus 0, or infinity over infinity. And again, to remove the indeterminacy, we remove the cos of the infinitude in the denominator. In this case, it is e to the negative x, which becomes infinite. So we will multiply and divide by its reciprocal. So we multiply and divide by e to the x, and then distribute. Okay, we obtain the limit of 1 minus 2 times e to the 3x all over 3 plus 2 times e to the 3x. And note that as x approaches negative infinity, 3x approaches negative infinity, so that its limit as x approaches negative infinity is 0. Okay, so this limit then is equal to 1 minus 0 over 3 plus 0, or 1/3. And that concludes this lecture. Again, please familiarize yourselves with the graphs of today's classes of functions in time for your next class. Try to work on the following exercises. If you have any questions, kindly contact your teacher or teachers. Thank you for listening. I hope you have a good day.